Good morning, afternoon, or evening, physics students. Last day of the fields unit today, just the outline for the quiz. Okay, a couple of things about next unit. Next unit is going to be a quick unit. It's the modern physics unit. As this Blackboard opens up, I'll describe here. And it'll be less, well, there'll be still some calculations in it, like using E equals mc squared and finding nuclear energies and things like that. But we will also have a little more descriptive type things in it as well. But it'll be a short unit, and I'm thinking for the last unit, we're going to just do a handed for that rather than a quiz as well. So this will be our last quiz, and then next unit we'll just have a handed, and I'll throw some questions on the final exam, a few extra ones on that unit, as it'll be near the end of the year anyway, and then we don't have to do two quizzes in there right near the end of the year. And that's kind of how I think we're going to do this one. Today is going to be the outline for the fields unit quiz, which we do have. And as the Blackboard's opening up here, the first thing I'm going to show you is the formula sheet on the front of the exam. So let me bring that up. Okay, so we'll just shrink this down here in a second. There we are. Okay, so if I bring this over, this is the first page of the exam here, which will be our formula sheet. Okay, so we have the electric fields exam. You can use a formula sheet. It's more than the electric fields. I typo there. It's the electric fields, just the fields exam, because we have magnetic fields and gravitational fields. Well, okay. As you can see, the first little bit is Coulomb's law here. That's electric fields. The electric field around a point charge K. Okay, K is the value above, right? The electric field strength on a test charge. Okay, we used Q prime. Okay, didn't put the prime in there, but it's the same idea. The potential difference or voltage, work over Q or energy over Q. Potential difference written in another way, where E is the energy and could also be work done. Okay. Then we had gravitational fields. We had universal gravitational law from Newton, gravitational field strength around planets, orbital period around a planet, orbital velocity around a planet. Okay, and then we had magnetic fields. And in magnetic fields, we had mostly diagrams, but we did have the one formula for magnetic force on a current carrying wire, where note that if psi here, if it's 90 degrees, you get the highest value of 1, gives you the highest force. Okay, so that's our formula sheet that we're going to use. Pretty straightforward exam in that way. Okay, so let's go ahead and flip over to what is on the quiz. Move this over, open our Blackboard up. Okay, so this will be our outline. Day 18 or whatever day it is. Outline for the quiz. Okay, this will be the outline for the fields quiz. Okay, so we have the formula sheet. Formula sheet is given to you, okay, with all the constants and everything that you just saw. Okay, and then we'll get into specifics. There's 8 questions on this quiz. Okay, it's not really that difficult. Okay, the first question is some explaining type stuff. Okay, so in number 1, is we have some explaining type questions. Okay, it's an explanation question. I'll also, called short answer if you're writing English or something like that. Okay, and it's going to be a two-parter. Okay, it's in two parts, so there's two of them, and it's 5 points, 2 for one and 3 for the other. Okay, what kinds of things can I have under the explanation question? First thing I can ask, if we're talking electric fields, and is I might ask, what are the laws of electric charge? Okay, like charges repel, opposite charges attract each other. Sometimes very large charges will attract neutral objects. Okay, negative charges move, positive charges don't move. That basically covers that. Okay, I might ask, what is the difference between Newton's view of gravity and Einstein's? View. Okay, so when we're talking about gravity for Newton, Newton sees it as the gravitational force is proportional to the mass of any two objects, and they're directly proportional that way, and indirectly proportional to the distance that the objects are apart. And he had an equation for it, and he saw it as a force, okay, that kind of thing. Whereas Einstein looked at gravity as an effect, and he looked at it as the effect that happens when you bend space or curve space, if you like, and then he used some analogies to describe that, like the trampoline effect with a bowling ball on it, making a divot in it, and that divot is kind of the gravitational force. Okay, those are the two views on gravity. Okay, we also might have charging by induction, charging by contact. Charging by induction, charging by contact. Okay, when you're charging by induction, you have a charged rod or object, a neutral object like an electroscope. What you do is you bring that object in close, you touch the object with your finger or ground the object with something, then you remove and then what happens is, as the charge object was brought in close, it separates the charge. You bring your finger in close, it'll either cause electrons to move off the neutral object or onto the neutral object, depending on the charge of the rod. And then you remove them both, the rod and your finger, and the electroscope will be charged. And charging by induction gives you the opposite charge of the rod. Charging by contact is where everything happens similarly, except instead of touching the electroscope, you take it and you, with your finger, you touch it with the actual rod that's charged, and it'll transfer charge onto the electroscope if it's negative, or take charge off of it if it's positive. And that's charging by induction or by contact. Another one that we might have in there, is you might have any of the right-hand rules with magnetic field. Okay, right-hand rules for electric force, right-hand rules for charge around a wire, and right-hand rule for a coil are the three that we looked at in there. Okay. I don't believe, but I'm just going to double check here if I had. That would probably be it, I think, for descriptions. There's nothing about orbital period or anything. We do calculations on that. Okay, so out of those 4 or 5 areas, well, there's just 3 right-hand rules and charging by induction and contact, and then Newton and Einstein. I'm going to pick 2 areas in there, depending on which exam I give you, as I have a couple of them made up for this. 2 areas, and you have to do explain what's going on. One will be worth 3, a little bit more complex, and one is a little bit more straightforward. So that's question number 1. Okay, question number 2. Okay, and this is where we're going to get into some drawings. Okay, where we did. So this one was worth. Again, I have. Let's see here. 2, 4. I've got 6 for question number 2. So these are sketches. Okay, worth 6 points. And these sketches will be dealing with drawing 3 different sketches. So you're going to get 3 different ones, 2 points each. Okay, what kind of sketches can I put in there? Okay, the first one is I can have any of the magnetic field sketches. Okay, so what are you looking at there? Under a magnetic field, you're looking at around a wire. Okay. You may be looking at in a coil or around a coil. Okay. You may be looking at those ones, and then actually those are the main 2 that we did, I think. The other one where we do the right-hand rule with magnetic force. So any of the magnetic field sketches or the magnet, we'll put in there, or the magnetic force sketch. And so you can have the magnetic force one as well. Not all of them are going to be magnetic fields, okay, but it's going to be a couple of those maybe. I don't know. We'll see, depending on which exam you get. And also, you could have some of the electric charge diagrams. Okay, so drawing the electric fields around 2 charges. Point charges, or around 1 point charge. Okay, so there's the electric field ones. Okay, gravitational stuff, we didn't really have any diagrams there other than the curving of space thing, but I'm not going to get you to draw a diagram of gravitational lensing or anything like that to worry about, okay? So those will be the main areas, the magnetic fields and the electric fields. Oh, and I guess you might have an electric field between 2 plates. But that one will probably be in a word problem. Okay. So that's probably it for you to worry about for that diagrams. And then we get into some of the calculations. That was worth 6. Okay. Number 3. Okay, here we get into some calculations. We're going to be looking at, in number 3, some calculations that deal with the electric force, Coulomb's law. Okay, so Coulomb's law type calculations. Okay, so we're looking at, in there, 4 points. I got 2 of them. Okay, so you'll be using Coulomb's law, the force equation, to calculate. So let's do an example here for ourselves. What is the calculate force between a positive 4.9 microcoulomb charge and a positive 15.2 microcoulomb charge that are 8.4 centimeters apart. And that I would have another one in there as well, maybe not calculating force, but maybe calculating a missing charge. Okay, so how do you do that? Well, we got to use Coulomb's law. So that'll be on the exam, obviously. You don't have to worry about it. So you want to try that one, you can. You can pause it and try it, or watch me do it. It's up to you. Okay, so when we do this one, we're looking straight at Coulomb's law. The force of electric charge is equal to Coulomb's constant K times first charge size and second charge size over R squared. Oops, the distance squared. Which we used R for. So we know that Q1 is 4.9 times 10 to the negative 6 coulombs. We have to make sure it's in coulombs. Q2 is equal to 15.2 times 10 to the negative 6 coulombs. Okay, and then we have the distance. Distance has to be in meters. So we got to change 8.4 centimeters into 0.084 meters. Okay, and then we can calculate it. And we know that the constant, which is given on the exam, is 9.0 times 10 to the 9. If you look at the top of the exam, that'll be there. So we go 9.0 times 10 to the 9 times 4.9 times 10 to the negative 6 times 15.2 times 10 to the negative 6, all divided by 0.084 squared gives us the force. Okay, and that's going to be in newtons. If we kept our units in there, the constant is Newton, meter squared, coulomb squared, and the meter squared cancels out, and the coulomb squared cancels out because of the two values of coulombs here and the two values of meters there when you square the meter. Okay, so let's do the math. 9, scientific notation 9, times 4.9, scientific notation negative 6, times 15.2, scientific notation negative 6. Okay, divided by 0.084 squared. So we get about 95 newtons. Okay, so there'll be two of those. One will be finding force more than likely. One will be finding either the other charge or the distance more than likely. Okay, so manipulating Coulomb's equation will be important for number 3. Okay, let's go on to the next page here and also check our time here. Okay, that's about 20 minutes. This may be a longer day to get through the whole review. You might have to chop it into 2 pieces, as I went through 20 minutes already. Okay, number 4. Okay, and there's 8 of them, so this is halfway through. Okay, sorry. Number 4, we're going to be looking at using the electric field equation. Oops, sorry, guys. Now, they might not be in this exact order, by the way, because I have a couple different exams that I've made, and some of them are numbered slightly different, but they have the same kind of questions on them. Okay, so what we're going to be looking at here is the electric field. Also, the gravitational field formula. So it's the gravitational and electrical fields, okay, formulas that in there, one each. Okay, so let's do an example of the gravitational field, because we already did electrical on there. So that's worth 4 points. What is the gravitational field strength? Of a moon that is, let's say, I don't know, 2.2 times 10 to the 24 kilograms. With a radius, average, we'll say, of, let's say, 2,450 kilometers. Don't know if there's such a moon that exists, but I'm just making it up. Okay, so that would be a gravitational field strength question. Okay, so we'll raise this up here. Okay, so if we're looking for our gravitational field formula is what we're going to be looking to use in this one. Okay, so if we, and you won't have to worry about memorizing the formulas, they'll be on the top of the exam. Okay, so the gravitational field formula and also the electric field formula, okay, will be on the exam. Okay, they'll be in different spots, obviously. Okay, the electric field one is KQ over R squared, if you remember from the beginning, and the gravitational one is capital G, that gravitational constant times the mass of the planet over R squared, which is the radius. So let's do that one. So the formula that we're dealing with is gravitational field strength equals capital G times the mass of the planet or object that we're talking about over R squared, the radius. Okay, the thing that's tricky is this has to be in meters because G is in meters. Okay, so we remember that G is in 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. So it's in meters. This is already in kilograms. We're good there. But this radius is not in meters. It's in kilometers. So we have to change the radius from 2450 kilometers into meters, which would be an extra 3 zeros for meters, multiplied by 1,000. 1,000 meters in a kilometer. Okay, once we have that, then we simply have the mass of the planet already given to us, and we just plug in the numbers. Two significant figures in this question. Okay, so going to work it out, the gravitational field strength of this particular planet is going to be 6.67 times 10 to the negative 11 times the mass of the planet, 2.2 times 10 to the 24 kilograms. Okay. And we have to divide by r squared, which has to be in meters. So this is 2, 4, 5, 0. That's a pretty big planet, actually. 0, 0, 0. I should have said that was the diameter, maybe. But whatever, that'll be fine. Okay, squared. Almost didn't square it there. Okay, so let's take our calculators out and crunch those numbers together. 6.67, scientific notation, negative 11, times 2.2, scientific notation, 24. Get a pretty big number. Divide by 2,245,000 squared. And I get 24.4 newtons per kilogram. So 24 newtons per kilogram. So it's about, about 2.5 times the gravitational strength of the Earth. And that's probably because I gave it a pretty big radius and a fairly chunky mass as well. Okay, so that is an example of field strength. We'll also have one of the electric field in there as well, so don't forget what the electric field one is, and that will be on the exam as well. So let's go on to number 5. Okay, so in number 5, we're getting into a calculation of orbital period and orbital velocity, okay, using those two. So number 5 is going to be a 4-pointer calculating of a satellite. So number 5, calculating orbital period. And velocity of a satellite. Okay. That's above the Earth or whatever, and you'll get all the constants you need. This is worth 4 points. Okay, so let's do an example of that. I'm only going to do half of it here. I'm going to do the calculating the orbital velocity, and the orbital period is a very similar formula. They'll both be on there. What is the orbital velocity of a satellite of 195 kilometers above a moon with a mass of, let's say, 3.4 times 10 to the 22 kilograms. And a radius we got to put in there as well. A radius of, let's say, I don't know, 4,250 200 even kilometers, question mark. Okay. That one. Okay, so the first thing we got to do is we got to get the formula for orbital period or orbital velocity, pardon me. So that'll be on the exam. So orbit, and I even put the words in there as you saw at the beginning when I showed the formulas. So orbital velocity is this one. An orbital velocity is equal to the square root of capital G, Newton's constant of gravitation, times the mass of the planet, or moon in this case, divided by the radius. Okay, so the first thing we got to do is we got to make sure that it's in meters because that's what G is in. So the mass of the planet we're fine with. In this case, it's the mass of the moon, 3.4 times 10 to the 22. However, the radius is going to equal 4,200 plus the height above the surface, 195 kilometers. So this is going to give us 4,395 kilometers, which we're going to have to convert into meters by multiplying by 1,000. Because that G has meters in it. Okay, now we apply the formula on the left here just by plugging our numbers in. Okay, so velocity, orbital velocity is going to be the square root of 6.67 times 10 to the negative 11, okay, and times the mass of the planet, which was 3.4 times 10 to the 22 kilograms, divided all by 4,395,000 meters. Notice it's not squared this time. Okay, and we're going to end up getting a meters per second when we do all this work. Don't forget to square root it. And don't forget that this square root goes all the way. You have to do all the stuff inside first before you square root. Okay, so taking our calculator out, we go 6.67, scientific notation negative 11, times 3.4, scientific notation 22. And then we divide it by 4,395,000 meters. Okay, and then we don't forget to square root that at the end to get about 718 meters a second. It's pretty big. Sorry, guys, excuse me. Two significant figures I should go, so maybe 720 meters per second if we do two significant figures. Okay, so that one has two problems involved as well. You'll have orbital period as well. Okay, I'm going to recommend maybe breaking this video in two. This would be a 35-minute spot. I have if you're on your own and you got lots of time, we've only got 6, 7, and 8 left to go, which will be about another 20 minutes or 15. Okay, so you might be able to get through it today. Maybe you'll have to kind of just put a little bit off for later. Okay, so number 6. Okay, number 6 on the quiz is going to be dealing with, sorry guys, I'm a little wore out this morning. Track meet was yesterday. For whatever year this is, this is 2018 here. If I'm using the same video next year, this was last year, but this is the first year I made them. So I was at track meet yesterday, a little bit tired. Got in early this morning to catch up on some physics videos. That's what we're doing here. Okay, so the next one is going to be one of those electric field questions with voltage and electric field. Okay, so question 6 is a 4-pointer as well, and it deals with electric field and voltage, or potential difference type question. Okay, similar to the one that I had on the assignment. Okay, it'll be a two-parter, just like on the assignment as well. It's not as big. It's only 3 points. These are fairly simple. Oh, the whole thing is fairly simple, actually. Okay, so let's do an example of it. Let's say we have 2 plates are, let's say, 0.18 meters apart. Okay, the period, the magnitude of the force well, let's say electric field, because it's an electric field question, not a force question. All right, is, let's say, 4,200 newtons per coulomb. Fine. Okay. Okay, so the first one is potential difference, or the voltage between the plates. All right. Okay, and second one is how much work to move is needed to move a, let's say, 1.1 microcoulomb charge. Field. Okay, so again, we're just using the potential difference equation, and we're just using the equation for work in an electric field. So what we do know here is we do know the electric field strength. And I'm going to put a little F so that we remember that's electric field, not energy. Okay, we know a distance. And that's it. Oh, and we know a charge in the field. Okay, 1.1 times 10 to the negative 6 coulombs. And that is it. Okay, so the first part is just applying a simple formula for the potential difference. Again, you won't have to memorize anything there. That's on the front of the exam. So if we look at the front of the exam under electric fields area, you're going to have the electric field formula, which with potential difference involved in it, with distance and electric field potential difference. So the potential difference, marker wasn't working, is just going to be the electric field times the distance. Boy, that's not that difficult, really, right? So 4,200 newtons per coulomb times our distance of 0.18 meters. Now, newtons is a derived unit, so when you work it out, you're going to get volts, which is another derived unit. So just all you have to do is there 4,200, two significant figures, times 0.18, two significant figures, 756 volts, which we should round off to two significant figures because that's all we have. So 760 volts. Okay, that would probably be the 1 mark part of it. The 2 mark part is probably going to be finding how much work is done. So we know that work done can be written, or it comes from the formula written on the exam like this. Okay, it says change in voltage equals work over charge. So we need to rearrange that to be work done is equal to change in voltage times Q. Okay, in our case, we had I'm going to use the original value of the full voltage so that no rounding happens till after the exam, after the calculation, and the microcoulomb charge. Okay, so we just take 756 times 1.1, scientific notation -6, and we get to two significant figures, 0.1234, sorry, 1, 2, 3 zeros, 8, 3 joules. Or if you want to write it with scientific notation, 8.3 times 10 to the -4 joules. Okay, that's number 6. Okay, again, this might be the second day you're watching because I'm kind of going through the whole thing. Okay, in one swoop today, or this morning. I like coming in early and doing these things in the morning, for the most part. Okay, so that was number 6. Number 7, we've got 2 more. Okay, now we're going to use that one formula about calculating magnetic force on a current carrying wire. We have to do an example like that. Okay, so we'll flip the page here. Maybe I'll move this up so that I'm not blocking it there. Okay, so second last problem is dealing with a 2-mark question. Really quite simple. Okay, this one, number 7, just so you guys know, I used similar exam last year, had lots of good marks on it, not too hard, but study up those equations, don't get confused between the equations, and you'll do fine. Okay, so number 7 is going to be a question dealing with using the formula for magnetic force on a current carrying wire. Okay, so that's going to only be worth 2 because they're not that difficult. Okay, so I might have a drawing of that in one of the sketchy things as well, so keep that in mind. But the formula one won't need a drawing for it. You just be looking at the equation, so it might go something like this. What is the magnetic field strength? Okay, on a, let's say, 24 centimeter wire, it's 2 significant figures, with 0.168 amperes flowing through it, or current, we'll say, that'll be easy. Oh no, I have to say amperes of current. I have to say that. Flowing through it. If it experiences .85 newtons force. Okay, and then we'll say assume current force current magnetic field and force are at right angles. Okay, so that means that theta is 90 degrees in that formula. Okay, so if we look at again, don't have to worry about memorizing formulas. That's not the point of doing physics. The point of doing physics is to predict what we would see and use those formulas and then think out of the box later on to develop more physics. Okay, so here we have that very, very last formula on the formula sheet, which is the force is equal to, looks like this. Force is equal to, we have the current times the magnetic field times the length of the wire times the sine of the angle between the magnetic field and the current. Okay, so we know that the force is equal to 0.85 newtons, that the length of the wire, we have to write meters, so that's 0.24 meters. The current is already in amperes, so we don't have to change anything there. Okay, and the magnetic field is what we're trying to find. Okay, and that's going to turn out Teslas if we keep all the proper equations in there, and that the theta is 90 degrees because it's right angles. Okay, so if we're going to rearrange to get the magnetic field, B, magnetic field, is equal to the force divided by all of these I times L times sine theta. So if we do that, we go 0.85 newtons over 0.168 amperes times 0.24 times 1. And that's going to give us our answer. So I'm going to do the bottom part first, 0.168, pardon me, times 0.24. Okay. Okay, get our answer, divide that into divided into 0.85, and we get approximately, what do we get here? 21 Teslas. Okay, let me just do that again. Okay, say. Yeah, about 21 Teslas, two significant figures. Okay, and that is 2 marks. Okay, question like that. It might not be finding magnetic field. It might be finding the length of the wire, or the current, or the force. Won't be finding the angle. That's the only one you won't have to worry about. Okay, the final question on there deals with a question of, what is it here? Gravitational force. Okay, Newton's gravitational force. Okay, so the last question, number 8, is 2 points. And it's using Newton's gravitational force equation. That will be the last one on the quiz, and let's say something like this. The gravitational force between two it's between a 290 kilogram object ball and an unknown object that is, let's say, 200, that's 220, let's go, so we have two significant figures. That is 220 meters away. Is 1.4 times 10 to the negative 9 newtons. what is the mass of the unknown object? Question mark. Let's fix this -9 up here. Okay, so again, you can try it if you want, and then unpause it later. If not, here's how you work it through. Okay, so we have a gravitational equation for Newton's laws. We know that the force of gravity equals G times M1 times M2 over R squared. We want to get one of the M's. So if we rearrange it, we got force of gravity times R squared. If we multiply it on both sides, equals G times M, we'll say the ball, times M of the unknown object. Okay, so then we just simply divide G and mass of the ball on the other side. So force of gravity times R squared equals G times the mass of the ball. And that's going to give us the mass of this unknown object. Okay, so if we do that, the force of gravity that we have is 1.5 times 10 to the -9. Okay, and that's newtons there, times R squared, which is 220 meters squared. Okay, and then we have G, which is at 6.67 times 10 to the -11 newtons per meter squared, kilogram squared. And we have 1 kilogram here of the ball, 290. That's going to give us the mass of the unknown object. So take your calculator out, do a little bit of work. So 220 squared is where I'm going to start. Okay, times 1.5, scientific notation, -9. Okay, then I'm going to divide out 6.67, exponent, a scientific notation, -11. Then I'm going to divide out 290. So we get a fairly massive object. I get mass of this unknown object is 3,753.3 kilograms. So if we want to go to significant figures of 2, that looks like the mass to 2 significant figures is going to be 3,800 kilograms of this other object. And that is the 8 questions you will see on the quiz. Similar to those, maybe in a different order a little bit, depending on how I change it up a little bit, depending on what version of the quiz you get as well. It might be a little bit different. Now that's a big, long video, so you might have had to break it into 2 while you're watching it, or you might have been able to watch it in one shot if you have a spare or a double or something like that. So that's our outline for the quiz. I'm going to send that out right now to your supervising teachers so that when you're ready to write it, you can write it.